In this video, we will be covering lesson 23 on properties of logarithms. And as we're going through these properties, keep in mind from lesson 22 that log base a of x means what is the exponent that you have to put on the base a in order to get x, whatever is the input to the logarithm. Our first property is that log base a of a is equal to 1. Anytime that the base matches what is on the inside of the logarithm, the answer to the logarithm is 1. Example, log base 5 of 5 is equal to 1 because 5, that's the base, raised to the first power, that's the answer to the logarithm, is equal to 5, what's on the inside of the logarithm. Another example is that log of 10 is equal to 1 because, and remember that when you see log written without a base, it's understood that the base is 10. So the base of 10 raised to the first power gives us what's on the inside of the logarithm, which is 10. Another quick example is that natural log, ln, of e is also equal to 1 because the base of the natural log is e, and if I take e to the first power, I will get e back out. Our second property is that log base a of 1 is always going to be equal to 0. Regardless of what the base is, if you have 1 on the inside of the logarithm, you will get 0. So for example, log base 1/2 of 1 is equal to 0, because if I take the base of 1/2 and raise that to the 0 power, I will get 1 back out. So anytime that there's a 1 on the inside of the logarithm, the answer to the logarithm is 0. The third property is the power rule, and the power rule tells us that if you have log base a of m to the r, so r is the exponent that is on m, then you can pull the exponent down in front of the logarithm and have r times log base a of m. So for example, if we have log base 7 of p to the 8th power, I can pull that exponent of 8 down in front of the logarithm and have 8 log base 7 of p. So anytime you have an exponent on something that's inside of your log, you can always pull that exponent down in front. Here's another example. Let's say I have log base 5 of x plus 2 raised to the 3rd power. That exponent of 3 is on everything inside of the logarithm. So I can take that exponent of 3 and pull it down in front of the logarithm to have 3 log base 5 of x plus 2. Our fourth property is the product rule, which tells us that if we have a product on the inside of the logarithm, that we can separate it into the sum of 2 separate logarithms, where each log has one of those factors. So log base a of m multiplied by n is log base a of m added with log base a of n. An example of that, let's say that we have log base 9 of 9y. 9y is a product that's on the inside of that logarithm, so I can separate it into the sum of 2 separate logarithms, log base 9 of 9 plus log base 9 of y. And then I'll go ahead and use the first property that we had on the first logarithm, since what's inside of the log matches the base, log base 9 of 9 is 1. So we have 1 plus log base 9 of y. Our fifth and final property is the quotient rule that tells us that if we have a logarithm of a quotient, we can separate that into a difference of 2 logarithms. Log base a of m divided by n is equal to log base a of m minus log base a of n. So an example of that, let's say that we have log of 3x divided by y plus 2. That's a quotient on the inside of our logarithm. We can separate that into log of the numerator and then subtract log of the denominator. Whenever you're using the quotient rule, make sure that whatever was in the denominator is in the log that is being subtracted, because subtraction is not commutative. It matters what order you do subtraction in. Let's begin looking at some examples where we're using the properties that we just covered to expand and simplify logarithms. In example 1, we have log of y squared. There's an exponent on what's inside of the logarithm. So we can bring that exponent down in front and have 2 log y. And that's from using the power rule. In example 2, we have log base 3 of 3xy squared. It's important to note that we cannot start with the power rule here because not everything inside of the logarithm has the exponent of 2 on it. If we were working with this, that's different because here everything inside of the logarithm has the exponent of 2 applied on it. And what we're working with, only the y is squared. So we're going to have to begin by separating this using the product rule. You can think of this as the product of 3x with y squared. So the product rule tells us that I can rewrite this as a sum of 2 separate logarithms, log base 3 of 3x plus log base 3 of y squared. That's from using the product rule. Then we can simplify that first logarithm even further because we still have a product on the inside of it. We have the product of 3 and x. So we will use the product rule again to give us log base 3 of 3 plus log base 3 of x. And I'll bring down my log base 3 of y squared. On that last logarithm, log base 3 of y squared, we can use the power rule on that logarithm now because only the y is inside of that logarithm and that's what has the exponent on it. So I'll bring that exponent of 2 down in front of that logarithm. And the last thing we'll do to simplify this is that first logarithm, we have the base matching what's on the inside of the logarithm. And one of our properties tells us that that is equal to 1. Anytime the base and the inside of the logarithm match, the answer to the logarithm is 1. In example 3, we have natural log of the 8th root of p divided by t. I'm going to begin by rewriting the 8th root with an exponent. So this is natural log of p divided by t raised to the 1/8 power. Remember that when you have roots, you can rewrite them as fractional exponents. Now, because everything on the inside of this logarithm has the 1/8 power applied to it, I will use the power rule to bring that 1/8 down in front of that natural logarithm. So I now have 1/8 natural log of p divided by t. And now we can use the quotient rule on that logarithm. So we have 1/8, and I'm going to be using parentheses here. Natural log of p minus natural log of t. It's important that you use parentheses here so that you see you need to distribute the 1/8 to both of these logarithms to fully expand this expression. So we have 1/8 natural log of p minus 1/8 natural log of t. In example 4, we will begin by using the quotient rule to separate this quotient that's inside of the logarithm. We'll have log base 2 of what's in the numerator, which is 16x, and then we will subtract log base 2 of what's in the denominator, which is yz to the 5th. Working with the first logarithm, we will use the product rule to separate that because we have the product of 16 and x. So we will rewrite this as log base 2 of 16 plus, product rule tells us to add, log base 2 of x. We'll also be using the product rule in the second logarithm because we have the product of y and z to the 5th. Remember, we cannot use the power rule on that z to the 5th because the 5th is only applied to the z. It's not applied to the y as well. So we'll begin by separating this using the product rule. And it's important here again to use parentheses because you will have to distribute that negative to both of these logarithms. Continuing to simplify, log base 2 of 16 is equal to 4 because 4 is the exponent that goes on 2 in order to give us 16. I'll bring down my log base 2 of x. And before I use the power rule on that last logarithm, I'll go ahead and distribute my negative. And I dropped my base 2 on some of these logarithms. Let me go in and put those there. The original base of this logarithm was 2, so all of our logarithms should have log base 2. So we have 4 plus log base 2 of x minus log base 2 of y minus, now I will use the power rule on that last logarithm to give me 5 log base 2 of z. In our fifth example, we really only have differences on the inside of this logarithm, and we do not have a rule. There is no rule that tells us how to separate the difference that's inside of a logarithm. So instead of trying to separate it with subtraction, we will begin by factoring the quadratic that is on the inside of the logarithm. Because if we can factor it, then we can use the product rule to separate it. So factoring 11x squared minus 32x minus 3, this factors into 11x plus 1 and x minus 3. Now we have a product of these two factors, so now we can separate this into log base 4 of the first factor plus log base 4 of the second factor. And there's nothing else we can do to simplify that, because we do not have a rule to simplify addition on the inside of the logarithm, nor do we have a rule to simplify subtraction on the inside of a logarithm. We can only simplify multiplication, division, and exponents on the inside of a log. We will begin example 6 with the quotient rule. We will separate this into the difference of two logarithms. In the first log, we have what is on the inside of the numerator, and in the second log, we have what is in the denominator, and we are subtracting those two logarithms. Very similar to what we did in example 5, we will have to begin by factoring the quadratic that's inside of the first logarithm. So we need two numbers that multiply to negative 30 and add up to negative 1. That's a negative 6 and a positive 5. So now we have the first logarithm set up to use the product rule, since we have a product of those two factors. In the second logarithm, I'm going to go ahead and rewrite the square root of m times n as m times n raised to the 1/2 power. That's everything that was under that square root has that 1/2 power applied to it. I'll separate the first logarithm using the product rule now. So we have log base 1/5 of x minus 6, and we are adding log base 1/5 of x plus 5. We can go ahead and use the power rule on that second logarithm, since that 1/2 is applied to everything. So we have minus 1/2 log base 5 of mn. I will bring everything else down. So I've gone ahead and brought down our first two terms of logarithms, and in our last logarithm we will be simplifying it, or rather expanding it, using the product rule, since we have a product there. Be mindful that you need to be using parentheses here, because we will have to distribute that negative 1/2 to both of these logarithms. So we have log base 1/5 of x minus 6 plus log base 1/5 of x plus 5 minus 1/2 log base 5 of m minus 1/2 log base 5 of n. A helpful hint is that anything that shows up in the denominator should be a log that's being subtracted. So we have that 1/2 log base 5 of m and that 1/2 log base 5 of n, and they're both being subtracted because they originally showed up in the denominator. So far, all of the examples that we've done so far using our properties have been us starting with a single logarithm, starting with one logarithm and expanding it into many logarithms. The next set of examples that we will be doing will be us starting with many logarithms and condensing them down to a single logarithm. In example 7, we will begin by using the power rule to send all of the coefficients on those logarithms back up to the exponents. So the coefficient of 6 will be going to the exponent of y. The coefficient of 7 will be going to the exponent of m squared. It has to go to the exponent of everything on the inside of the log. and the coefficient of 4 will go to the exponent of p. I'll go ahead and simplify that. M squared to the 7th power. Rules of exponents tells us that we combine those exponents by multiplying 2 times 7 to get 14. And then looking at the first two logarithms, they are subtracted from each other, so we will combine them into a single logarithm using the quotient rule. So we have log base 6 of y to the 6th divided by m to the 14th. And then I'll go ahead and subtract that second logarithm, and then we will again use the quotient rule because we have two logarithms that are being subtracted. So we have log base 6 of y to the 6th divided by m to the 14th, and that is divided by p to the 4th. But you should not leave your answer like that with multiple fractions on the inside of that. We know that we divide fractions by multiplying by the reciprocal. So the p to the 4th will end up in the denominator with the m to the 14th. And that is our single condensed logarithm. Again, you'll notice that the logs that were being subtracted, what was being subtracted was the 7 log base 6 of m squared and the 4 log base 6 of p. Everything we got from those logarithms ended up in the denominator. In example 8, we will begin in the same manner by sending any coefficient to the exponent of that logarithm. So the 3 will be sent to the exponent of 2a. Make sure that you're using parentheses there to make it clear that the 3 is the exponent on both the 2 and the a. There's a difference between not using parentheses. This would be incorrect. The 3 needs to be applied to both of them. There's no coefficient to send to the exponent in the second logarithm, and in the last logarithm I will send the coefficient of 8 to the exponent of b. I'll go ahead and simplify the exponent in that first logarithm. I need to apply the exponent of 3 to the 2. 2 cubed is 8, and a cubed is simply a cubed. I'll bring down what we have in our second logarithm and in our last logarithm. There's nothing to simplify there. We'll begin by using the product rule to condense the first two logarithms, and we're using the product rule because these are added. We use the product rule when we're adding logarithms. So we have natural log of 8a to the 3rd multiplied by 4v. And I'll go ahead and bring down that last logarithm. Before I condense any further, I'll simplify what's inside our first log. 8 times 4 is 32. So we have 32a to the 3rd v. And then we're still subtracting natural log of b to the 8th. Now we will be using the quotient rule to condense those two logs into a single logarithm. And we're using the quotient rule here because these logarithms are subtracted. So we have natural log of everything that was in the first log going in the numerator and everything that was in the second logarithm going in the denominator. And so now we have that condensed down to a single logarithm. In example 9, there are no coefficients to send up to the exponents. Both of these logarithms have a coefficient of 1 and they are added together. So we will begin with the product rule. We use the product rule when we have addition between our logarithms. So we have log base 3 of the product of those two factors, x minus 2 and x plus 2, which now we will multiply together. Foiling that out, we have log base 3 of x squared minus 4. And we have condensed those two logarithms down to a single log. In example 10, we have coefficients that we need to send up to the exponent, so we have to begin by doing that. We cannot use the product rule, we cannot use the quotient rule if we have coefficients. If we have coefficients, we need to begin by using the power rule. So the coefficient of 6 is now the exponent on y. The coefficient of 5 is now the exponent on x squared plus 2. And the coefficient of 3 is now the exponent on p minus 6. Now we will take a look at our first two logarithms in this expression that are being subtracted. Because they're being subtracted, we're using the quotient rule. what's inside of the first log goes in the numerator. What's inside of the second log goes in the denominator. I'll bring down the addition of our last logarithm. And because it is addition, we will be combining these two logarithms using the quotient rule. Oh, excuse me, no, because it is addition, we will be combining these two logarithms using the product rule. So we're multiplying what's inside of the first log with what's inside of the second log. That p minus 6 to the third is going to end up in the numerator with the y to the 6. We multiply fractions straight across the top, straight across the bottom. You could think of this as p minus 6 to the third over 1. And so this is our simple condensed log. Again, same pattern here. Anything that was being subtracted, we see showing up in the denominator. Any logarithm that was positive, we're seeing those pieces show up in the numerator. Example 11, we will begin by sending our coefficients up to the exponents. So we have log base 23 of x to the 1/5 power minus log base 23 of y to the 1/9 power. To make this a little bit neater, I'll go ahead and rewrite those fractional exponents as roots. X to the 1/5 is the same as the 5th root of x, and y to the 1/9 is the same as the 9th root of y. Now we have a difference of logarithms, so we condense them using the quotient rule. So we have log base 23 of the 5th root of x divided by the 9th root of y. And that quotient is what is inside of our single condensed logarithm.